Good morning or good afternoon. My name is Isel Grau, and today we are presenting our work titled On the Performance of the Non-synaptic Backpropagation for Training Long-Term Cognitive Networks, which is actually a collaboration among several researchers from the Universidad de Talca, Hasselt University, the Free University of Brussels in Belgium, and Tilburg University in the Netherlands. So, the modeling and simulation of complex systems allow experts to explore the outcome of hypothetical scenarios before they are observed. The behavior of complex systems is challenging to model due to dependencies, nonlinearity, and feedback loops. Fuzzy cognitive maps allow to model complex systems and enhance the original model with the aid of historical data. However, their learning algorithms either produce poor results or override the knowledge provided by the expert during the modeling phase. Therefore, the main challenge of these models is how to train the network using both expert knowledge and historical data. To overcome the FCM's drawbacks, we propose in previous works short-term cognitive networks and the non-synaptic learning. Instead of adjusting the weight matrix, the non-synaptic learning focuses on the transfer function parameters controlling the activation of the neurons. This principle allows experts to inject domain knowledge directly into the network in the form of weights or constraints on the neurons' activation values. And yet the model is able to produce low simulation errors. And in further work, we proposed long-term cognitive networks, which handles longer dependencies among the variables. Long-term cognitive networks use non-synaptic backpropagation as learning algorithm, but this algorithm might fail when dealing with very long dependencies, since the error that arrives at the first abstract layers is rather weak. If this happens, then the network will stop learning. Other studies about backpropagation algorithms have shown that propagating the error backward through a random channel, or suppressing the deep backward pass are suitable options to bring the error signal into the first layers. So in this work, we study the performance of the non-synaptic backpropagation learning algorithm for long-term cognitive networks models under the hypothesis that the backward pass might not be needed at all. Overall, our paper makes two main contributions. The first one is that we propose three variants of non-synaptic backpropagation algorithm, and these three variants modify the error backpropagation process in different ways to obtain lower simulation errors. Secondly, we conduct several simulations using different pattern completion problems to investigate whether the backward step is needed at all and what is the contribution of each sigmoid function parameter to the learning capability of long-term cognitive networks. As mentioned before, the non-synaptic backpropagation optimizes the parameters of the activation functions of the neurons, instead of optimizing the weights as is normally done in backpropagation. This allows to preserve the knowledge represented in the weight matrix, and this weight matrix is important to preserve because it was provided by the experts when modeling the complex system. So the activation function that we use is a generalized sigmoid function which has 4 parameters: the slope lambda, the offset h, the initial condition q, and the skewness v. In backpropagation, it is usual that the weights from the forward pass are used during the computation of the network error in the backward pass. But some studies from the literature suggest that this symmetry might not be needed in deep neural networks. So with random non-synaptic backpropagation, we replace the weights in the backward pass by a random Gaussian noise based on the original weight, as is pictured here in this formula. And in this way, we study whether having the original weights is needed for obtaining a good performance in the context of non-synaptic backpropagation. A second alternative of non-synaptic backpropagation is the skipped version of this algorithm. In this alternative, when we update the parameters of a certain hidden layer, we use the partial derivative of the total error with respect to the neuron's output after a number of iterations. So we skip a number of abstract layers in the backward process such that we can deliver the error signal directly to the current abstract hidden layer. And this method can be convenient when learning very long dependencies, as the gradient tends to vanish or explode. So the error signal that reached the first abstract layers is not informative enough. And finally, the third variant that we propose is called random skipped non-synaptic backpropagation. And in this one, we tried combining both strategies in the algorithm. So during the backward pass, we replace the weights by normally distributed random numbers, while we also perform the skipping operation. So for the experiments, we use a set of tabular classification datasets, and 35 of them to be precise, and we adapted these datasets to the simulation problem where we need to predict the values of some variables from the values of others. This is a type of prediction we are doing here. The number of variables ranges from 3 to 22, whereas the number of instances goes from 106 to 625. These datasets are relatively small, as usually happens in real-world scenarios of complex systems where the expert can provide a limited number of training examples. The performance is measured using mean square error, and we do this through a tenfold cross-validation. The learning rates and the momentum are optimized during the learning process, and also the number of epochs we use for training is set to 200, while the number of abstract layers is set to 5. So, in our experiments, the first thing that we do is that we compare the non-synaptic learning variants in terms of mean square error. So in figure A, you can see the best simulation error, and in B you can see the median simulation error obtained by each algorithm across all parameter settings. The simulation these results support the main hypothesis of this research, which is that backpropagating the error signal through the abstract layers is not necessary to bring the error of the first hidden layer. And we conclude this because the methods implementing the skipping operation perform better in general. These comparisons are supported by statistically significant differences. Additionally, we also study in our experiments what is the contribution of each sigmoid function to each sigmoid function parameter, to the learning algorithm. And the figures here show the average mean squared error when learning 1 in A, 2 in B, and 3 in C versus all sigmoid function parameters. So in figure A, for example, you can see that the model obtained higher errors than the baseline if only one parameter is adjusted. Here, the baseline is considered to be when we optimize all parameters together. And from figures B and C, you can observe that the parameter Q doesn't contribute significantly to the algorithm's performance, so we can conclude that we can safely remove this parameter from the non-synaptic learning algorithms to lighten their formulation. So, in conclusion, we want to remark some points. We contribute 3 variants of the non-synaptic learning method to train long-term cognitive network-based models for simulating complex scenarios. We found out that the backward pass is indeed not necessary to train the long-term cognitive network in the non-synaptic context. Instead, we can bring the error from the last abstract layer to the current hidden layer without losing performance. We also found out that the sigmoid function parameter related to the initial condition, which is Q, doesn't contribute significantly to the algorithm performance. And instead, the most critical parameters are the function slope, lambda, and its offset h. These findings open new research avenues toward training recurrent neural systems with less effort. Thanks for your attention, and we are open to questions.